the creation of the dam, the river runs out of sediment really fast. What happens if we have migration? And this is just for the lower Elba below the two dams. Well, it actually runs out of sediment really fast. Remember, our exchange rates were really, our exchange distances were very long. So actually, we don't get a whole lot of supply from the floodplain. But there are some interesting features that come up here, and I think I probably have enough time to go through a couple of these. One of the important ones, and this gets down to the size-specific nature of these calculations. Oh, sorry. Let's see if that'll come up again. I'm going to plot D50 and cumulative bed change for the case with no migration and the case with migration. There we go. With no migration, the cumulative bed change is about 10, 12 centimeters, and the bed coarsens up really, really fast. When you have migration, I'll do it again. Here we go. The bed still coarsens up, but not by quite as much, and there's actually a little bit of down channel, a little bit of down channel change there. Let's look at that again. So you have a little bit of trend there, but look how it keeps incising over, through the whole 100 years of the run. What's happening is we're actually moving material from our paved river back into the floodplain and replacing that with material that's a little bit finer, so there's this continual exchange process that allows the river to incise more than it otherwise would. Okay, and you can actually see it here. This is, don't look at all of the details here, but look, this is migration rate on the x-axis. This is bed elevation change, or D50 on the y-axis. You get a finer bed that incises more if you have migration. Okay? I'm going to skip that, and I'll skip through that. I'll end the talk just by going through a little bit about how they did the removal here. This doesn't have a whole lot to do with the size-specific transport. Two dams, both removed by moving back and forth and carving out a part of the dam for a while and moving to another part of the dam. The larger of the two dams, Lions Canyon Dam, Concrete Arch Dam, was removed by equipment on a barge. This is what happened over 2011 to 2012. It took until actually the end of 2013 to get down most of the way down, and actually they blew out the last part of the dam just last summer. So it sat there with the final 20 meters or so on Lions Canyon for a while. And I think maybe I won't tell you the whole story. I will tell you that it got finer as the pole started moving through. This was before bed material even entered. And by a factor of, I don't know, B went down from maybe 7 or 8 down to 3 or 4, so it became quite a bit finer in the bed. A lot of wood and other material was released, and this also caused the exchange. The channels widened a bit, so there's widening and migration as part of this exchange process. And I think I will show you the video. It only takes a second. Flooding it's activated the floodplain more than it was before. The bed abrated by about a meter. This part of the floodplain would not have flooded historically. You could go along the trees and there was no sediment in the moss on the trees, but now it's active because the river's abraded, and that's raised the bed elevation and activated the floodplain. Okay, high energy floodplain too. Okay, so observations. There's a lot of bed material stored in off-channel deposits in natural rivers, and we should be thinking about that. And as long as they're laterally active, you can access that material. So some rivers may be sensitive to what's deposited in the bars and what's eroded to banks. So the size distributions of each of those is probably important in a lot of cases. And floodplains can be long-term sources. I didn't show you another case, but if that lower Elba had been much longer, another 50 kilometers, and you probably could have resupplied most of your sediment to the channel simply by the channel accessing that deposit. There are lots of modes of adjustment, and lateral change probably has important feedbacks on morphology and sorting. So I think I'll leave it there, but I do think that it leads to a series of research projects that would be worth doing, particularly related to size distributions in banks and bars.
Okay. Hello? We have now time for questions.
Well, I don't think they probably ever get there, but if there is an equilibrium, it would be this idea of a dynamic equilibrium where averaged over an appropriate amount of time, influx and outflux would be roughly equivalent, and that can apply for any box in a box model. As long as there's an inflow side and an outflow side, you would be at equilibrium where the inflow equals the outflow.
So by size as well. So
Yeah, right, good side.
you
Well,
move back and forth across the floodplain,
mhm.
and there'd be no net change in the river, in the floodplain, the terrace.
There would be a lot of change in the river and floodplain, but the material eroded would be replaced somewhere else. Yeah.
More questions?
Thank you for a very nice talk. Could you move to slide 31? It's the schematization slide.
This one?
Yes, it's probably one of those steps.
Okay.
But in one of those schematizations, you show that when the main channel, when the deepest part, when it degrades,
Yes.
then the lowest elevation of your floodplain also goes down.
Yeah, so
So
we,
so that would mean that you're taking in substrate sediment into your floodplain sediment.
that's right.
But is this just an artifact of the schematization, or does it also have a physical meaning?
I think that it has a physical meaning. So that would be, let's go back to, will you work with me going the other direction? So rather than it going down, let's imagine that you had graded, okay? If that was the case, let's go back to one of these first slides that I showed. All right, almost there. Here, okay? This was a case where you actually have gravel and cobble at the very toe of the upper bank, but on the opposite side you have gravel and cobble that's actually a bit higher. Okay? So in this case, so you asked about the river degrading. Let's go the other way. Let's say the river was grading. And let's say you build a cobble deposit that's yay thick. But over the time that it takes for the river to come back to that site, the river has graded, let's say, 20 or 30 centimeters. Now you would not be able to access all of that deposit when the river migrates through. Not all of that gravel and cobble would be available as beds material to move down to the next bend because you wouldn't erode necessarily all of that material. Some of that would be below the thallway now, whereas it hadn't been before. So, and if you're going the other direction, it would be the opposite, presumably. Now you would have, if you had been degrading, let's say you degrade a meter over the time that it takes for the channel to come back to that point bar that you see on the bottom, then that point bar deposit would look like it's a meter higher than the thallway, than it had been when it was deposited. So there would be now more material to erode, more coarse material to erode.
Maybe I'm misunderstanding. Could you move back to that sketch?
Yes.
Because I would think that there's, I mean, if you grade, if the deepest part grades, does the lower elevation of the floodplain, does that go up with the elevation of the?
Well, again, what we're trying to do is
I mean,
find.
then you lose sediment to the substrate, and has the same grain size distribution as the floodplain. So your floodplain grain size distribution would not change. So there's no problem. But if the deepest part degrades, you're taking in substrate sediment into that floodplain box.
Yes.
So the floodplain box changes.
That's
grain
right,
size
and that's the whole reason this is not the best box to use. This is why we have a floodplain zone and a channel zone of the substrate. So that you would be, because presumably the channel zone, the active layer is coarser than the average substrate far from the channel. Let me go back to the original box where it's just a simple set of two boxes here. Okay? So if the active layer here, the A, on that graph goes down, then you should be, in effect, moving material from box S3C into box A, and you should be moving material from box S3F into box F. So that's what we're saying. Is that consistent with what you're?
Yeah. So you're changing the grain size distribution of F.
Yes, that's right.
Yes.
Yes.
Which you may not want to do.
Well, it depends on what's available below the channel. I mean, below the active. That material will at some point be available for the channel to erode through lateral change processes, or whatever exchange process you want.
But why does that make the floodplain top or down? Is that what you're asking? I don't understand either. When you show that the actual height of the floodplain drops when the river's cutting down.
Oh no, I'm not saying the height of the floodplain should not drop. Let me go back to the cartoon. If you go to the cartoon, the height of the floodplain is not changing. So let's say, again, we go into sediment deficit. We cut off, the dam comes in, it cuts off sediment supply, so you remove sediment from the active layer, of course it gets coarser, but it also incises some. So next time it erodes, it's going to be able to hit a floodplain. We have to go to the next box. Here we go.
And then did the floodplain just get lower?
No, the top of the pink box didn't change. So this is like that in an initial toy model. So in that toy model, when you incised, you now have a higher terrace. You can create terraces by incising.
Yeah.
And now when you erode into a terrace, you have more sediment for a given lateral change than you would have when it wasn't a terrace and it was just a low surface. Okay? So that's what we're creating here. When you cut off sediment supply, the channel incises, and it's like you're creating terraces that you're eroding into.
Right, go back one step. That's why I'm getting visually there. You have this brown layer that disappeared.
Oh, this is overbanked. Oh, maybe I didn't draw the cartoon very well. That material doesn't really disappear. That's moved into the box, and it stays. It does not. The box elevation doesn't change. So if you're moving overbanked material onto the box, that adds to the volume of the box and can actually raise the elevation of the floodplain. Yes.
More questions?
Just a comment in terms of sort of integrating ideas. Takebara-san was talking about the IRIC suite of models, which has a wide variety of capabilities for modeling river mold dynamics. I don't know if the models yet have the capability to account for things like channel migration, channel floodplain interaction, including some of the effects that you've shown. And I'd like to know what the prognosis is for getting those into IRIC type models, and from Wes's point of view, how important you think it might be to do so. So a little bit of discussion might be worthwhile.
Shall I start?
I'm not sure if Rush is.
Yeah, I'm not sure I see him. So I can give you my 2 cents on that, though.
He's not here.
No, I think it's.
Yeah.
Yeah.
But it is a good conversation, and I was hoping to, I ran out of time, but you can do much of the same things that I do here with a more complex 2D or 3D model. And I actually tried that on the Elwha, and it takes 12 hours just to run the hydraulics, if you want to run the whole post-dam period every day for the last 3 years. And that's with the 10-meter grid size. It may not be the best model, but it was actually, I was using a Caesar, which is a simplified physics model. And so first of all, I think there are computational issues with that. Second of all, you have to know whether your model is approaching a realistic equilibrium, and I don't know that that's been shown with most of the 2D models. So if you're talking about these complex floodplain processes, where flow can go really fast down between trees and knock trees over, and you get storage in the lee of those, I mean, it's a really complex place. And I'm not sure whether we'll ever be able to do a really good job with 2D models doing all of that. So that's my, and then also, the dynamics of the channel depend on the size distribution of what's being eroded. And while you may be able to do a decent job in a good 2D model, getting the erosion part right, how do we have any idea whether the gravel layer is 10 centimeters above the gravel layer in the bar? I mean, it's going to be really difficult to model the height of that bar using 2D modeling approaches, or 3D or whatever.
Well, I'm not actually suggesting that people should rewrite a 2 or 3D model to get in all the details, but that rather maybe for some of the 2D models, it would be nice to get in bed, bank, floodplain exchange parametership.
Yeah.
And the issue here, again, we don't get Takeba-san here to comment more, but from your point of view, in the rivers that we have talked about today, for example, in Minnesota, for example, the Elba deposits. How wrong would you get the problem if you wrote a more dynamic model where you did your sediment balances based on fixed banks and no migration and no exchange? How wrong would you be?
Well, in the case of the Elwha, where you have 500-kilometer distances for the mud, you probably would do totally fine if you were to, but you may not care about the mud anyway because that's so long. If you cared about the storage of the cobble, I think you wouldn't do particularly well because it only takes roughly, on the order of 5 kilometers to bring in something similar to the load, right? So that it would depend on the size, and so it would depend on how much of each size you have in your system. And it would depend on those exchange fluxes. So if you have a system that's not migrating very fast, then you probably would be okay.
Of course, if it isn't migrating at all, you'd be just fine.
Yeah, if it's not migrating at all, it's totally fine. But I think the natural state of rivers is that they do, and that they have multiple modes. I didn't talk, my cartoon would have blown up if I had talked about widening and narrowing, but that's another exchange process that you can incorporate into we actually wrote it into the mast model. So simply having a pulse coming through widening, that leaves behind material that may not be accessible immediately to the channel, but at some point later on when the channel shifts into it, it will be. Right, so I agree, and on the Minnesota River, that could be accounting for a significant amount of the bed material flux.
Other questions?
I can say from here.
Okay.
The vegetation can play an important role in this. Have you estimated the effects of the vegetation on these sediment dynamics?
Yeah, that's a good question. I have not, but I've wanted to for a while. I think it would affect the partition. So there's a rough, you have to specify a friction parameter on the floodplain. And so we could play around with that friction parameter as one way of, so in the same way that Hiroshi had done that, I think, in the braided model. You could do something like that here as well. But the problem is you're averaging over such a large area anyway. I haven't been quite sure how to do that or how strong the effect would be. I think that it would be there, but again, this is trying to characterize sort of averages across the whole system at various stages of vegetation succession, all in one box.
Yeah, so I have a question. I'm curious about what you were saying with the sediment supply to channels downstream from dams because of channel migration. And I kind of have two main things that I'm thinking about in what's really a much more complex system. But the first one is what you mentioned at the start. There are a couple studies out now that show that increased sediment flux correlates with increased channel migration rate. And so if there's not much sediment input to the earlier cells in the model, then I would imagine that there would be some sort of feedback as the sediment starvation wave goes downstream into how far that can be sustainable. And so I guess my first question would be, I'd be curious about some sort of timescale of that compared to the timescale of a reservoir lifetime, for example. And my second question, which kind of goes along with that, is that if I imagine just in a long-term mass balance sense, if you're migrating, but also depositing behind that, then it's a net zero. So overall, you have to, I think, widen to be able to have a sustainable increase in bed material. Well,
Yeah, so I'll actually use this as a chance to get to the slide I didn't have a chance to get to, but this is a longer system where this is representing the Ain River in France, where I actually spent some time building the model. This is showing that wave that you're talking about downstream of the dam, but now this isn't just a 10-kilometer reach, it's 40 kilometers. And it incisors, and because it incisors, you get a lot of material from the banks. I tried to do just what you said, which is see whether you could represent, whether reducing the lateral change rate would dramatically affect the supply. Look at the top left chart, it's the net bed change, and then the bottom left chart, which is the sediment flux in the river. The original flux is pretty close to what is there on the right. And this is using a constant migration. It turns out if you make migration a linear function of the sediment supply relative to the initial supply, you still get pretty similar curves. I was surprised by that, and you get that because it just incisors a little bit more. You get a slightly higher terrace, but you can still make up the sediment.
so actually, I would wonder if there would be another feedback associated with the terrace, because if the terrace were made of some material that would be bed material, then it would take longer for the river to incise laterally through that, and so perhaps that would end up being a constant anyway, even with a higher terrace, so that feedback would not exist as you.
Yeah, that could